I'm Ben Murrell at Karolinska in Sweden, and we're based in a microbiology department, which is a bit interesting for this work. But these days we're doing purely computational work. Um, the lab are all uh, they're mostly undergraduate students that have been working on this. And the main contributors here were Lucas and Hedwig on driving some of the theory work, and then the rest either contributing to bits of empirical results or bits of the sort of ecosystem that we're building to use here. Um, so
Amazing.
if there are like there might be some questions that I'll refer to Lucas or Hedwig depending on the details. So okay, I'll dive right in. Um, the the kind of motivating problem here is that I find it a little bit annoying that when you want to sample from most of these classes of flow matching or diffusion models, you have to say exactly how long something must be in advance, how many elements there must be in this sequence. There's a few exceptions, but almost all models require that to be pinned down. Um, and uh, the kind of motivating examples where the problem shows up the clearest are if you want to generate an infix, so some bit of sequence that's flanked on both sides, and the problem we care most about is protein design in the lab. I mean, and one example there is if you want to design the CDR3 of an antibody, most current models require you to say like how long the CDR3 should be before you design it. So sure, there's ad hoc strategies to work around that, but the goal of this is to really try and solve that problem directly. Um, and by the way, feel free to stop me, interrupt if you have questions. I'm happy to keep it quite interactive. So so to go through this, I'll kind of give an overview, like an intro to generator matching. It'll be quite informal. Then I'll talk about some previous methods that handle state dimension change, and then I'll segue into our particular construction, and talk about what we've done and how it seems to behave. Um, so the kind of framework we're working in is called generator matching. This is an extremely high value paper. If you haven't kind of internalized it, it's a really good one to get on top of, because it lets you do so many things. Um, and the basic idea is it's generator matching is just flow matching, but more general. And the construction is probably what you're all familiar with. So I won't spend too much time, but you basically start with an X0 sample from a noise distribution, and uh, you train a model that will convert that into a sample from your data distribution via some stochastic process. And so the point of generator matching is that it works in general spaces, so it encompasses a large class of sort of diffusion and flow matching models um, that that can all fall within that framework. And so how this works is like if you're looking at this, it'll look just like the flow matching story, except that it works for other kinds of processes as well. You have your data, which we call X1, right? You have a simple, easy to sample from prior distribution, which we call X0, and you specify a conditional process that first samples a latent Z, right? And that latent Z, it typically includes one of the X1 elements from the data distribution. We'll explain that this turns out to be a very useful thing more generally. So that latent Z has an X1 data distribution kind of tied to it, right? And then you define a stochastic process that is conditioned on Z that transports a sample from your prior to a sample from your data distribution. Well, in particular, the X1 that is associated with that Z element, right? So I'm going to be informal here, and when I say a stochastic process, I'm just going to say the distribution over the next little time step of your state given the current time step and Z, right? So that's this conditional process. So given a Z, it turns an X0 into an X1. Then how generator matching works is there's another marginal process where what this involves is that it's the average of this step, the small time step that is weighted by the posterior distribution over z given x, t, and t, right? And the whole trick with generator matching, which is the same as flow matching, is that this conditional process marginal at any time over xt matches the marginal process marginal at xt. So this lets you use the conditional process to draw training samples very efficiently because you get to kind of pick what your conditional process looks like. And the trick is that you train a model to directly learn what this average step looks like. Okay. So in the flow matching case, the step is like a straight line towards your x1 point, but the point of generator matching is that this can be kind of any process you want to write down. Now, when I say that the average, this is actually hiding some complexity, and it's there's a useful heuristic for reasoning about what that average means for different kinds of processes. And if the one I like is if you imagine stacking up multiple different steps that all involve a different Z and looking at what their cumulative effect is, it's a good way of understanding what that average will look like. So if you have a pure drift process, and each different Z is taking you in a different direction. When you take the cumulative effect of those, you wind up with a sum of all of the vectors that you stepped on, right? And that means that if you have a sum over that amount of time, it's equivalent to just averaging the velocities. If you have a drift and diffusion process, every step is a sort of drift offset and then a sample from a Gaussian distribution. And like the variance of the Gaussian might be something that changes the model. And if you look at the cumulative effect, you wind up with the average of the drift vectors and a draw from a Gaussian whose variance is the sum of the variances of the component Gaussians. Um, and so that's how your variances average in your drift diffusion process. If you have discrete substitutions where you parameterize a change from one discrete state to another via rates, if you think about the cumulative effect of rates of events, the effect is this equivalent to the sum of the rates. Um, and then the kind of interesting case that will kind of dive us into our first example is if you have continuous jumps where your state is unchanged, except when you have a jump event, you change to some distribution that depends on your Z, right? The cumulative effect of those is not like let's say the jumps were individually Gaussian. The cumulative effect of those is not another Gaussian, it's actually a mixture of Gaussians. Um, so when you have jumps in continuous space, your average winds up being a mixture over the target distributions uh, that you can jump to. Um, and so that's kind of generator matching with some heuristic arguments for how to reason about what this average will look like in a nutshell. And that dives us into the first method that I'm going to talk about that tried to kind of tackle this problem, which is called trans-dimensional generative modeling via jump diffusion models, and I'll just call this trans-dimensional jump diffusion for short. Um, and uh, what's like this is a really nice paper, and what's interesting here is this is diffusion. It's a diffusion paper, so they do everything backwards. So the conditional distribution they write as, in the reverse direction where you start from your data and you introduce noise like this. I'm writing this sort of in flow matching direction. So x0 is on the left and x1's on the right and x1 is still from your data, but this is not how it's set up in the paper. Um, but how transdimensional jumps works is you have this noising process that takes every element in the data distribution and diffuses it by noise, and then with some rate it gets deleted, right? So here's an atom and it moved around and it got deleted, and you can kind of think this is a little representation of the distribution it could have landed at when it was deleted. There'll be some variance there because the thing is diffusing, right? So what's interesting is when you think about that in the denoising direction, which is the direction the model actually has to learn, right? You're starting from one element and you're perturbing its location, like this the value of the state, right? Its position, if it's an atom, and then you're inserting an extra atom into your state, right? And then the question is, what does that insertion look like? How do you parameterize that insertion? So if you think about it, like what the current state will look like is at some time t, you've only seen like you only know what the current this is sort of the history of the generative process moving forward from in this direction. And you've got a state that's here and a state that's here, and that sort of pins down what the future can look like. And let's be generous and say it exactly pins down where these atoms wind up. uh, Now the model has to decide to insert something new, right? So if you think about it, the original example that I showed had an extra hydrogen over here, but that in 2 dimensions, that hydrogen could easily have been over here as well, right? Which means when the model has to consider an insertion, it must model a full distribution over where these things can insert. That's going to be a mixture over every possible value from the data distribution that's compatible with the current state. So that's going to wind up looking like, in this case, two Gaussians, the one Gaussian that would plausibly transport you to here and the other Gaussian that would plausibly transport you to here, right? And it's basically that's a result of the same argument that when you have a jump into continuous space with a jump process, the thing you get the cumulative effect of that is a mixture of all of the different locations you could jump to, weighted by each set. So this gets like worse in 3 dimensions. If you imagine like the position being, the atom being here or here, it's actually going to be the sort of legal space it could be is going to be in some circle around, and then the distribution you have to jump to spawn a new atom if you want to match your noising process is going to be some like smeared circle of Gaussians. And the more examples you think through, kind of the worse this gets. And so to model this correctly, to actually have the marginal match the conditional, you need the model to be able to output like an arbitrarily flexible mixture of Gaussians, um, which is a challenge. Like there's not something that's easy to parameterize a model. Yes, go ahead.
So I do not quite see the problem here. You're saying that at a certain time, when you spawn in a new atom, for example, or you spawn in new dimensions generally, then this for some reason would now be harder than modeling the. Are you saying that if you are at a late point in your denoising process and you have something that should already look quite like data, then spawning in the new dimension will mean modeling like a large distribution already, a complicated distribution already,
Yes,
compared to when you spawn in something at the beginning, which then can still be refined a lot.
yes, that's right. So
I see.
So basically, to work around this, you have to control the spawn rate to make sure things spawn very early, where all of the detail has already kind of been convolved by a large enough Gaussian that it looks Gaussian itself. But what that means is you can't have a lot of structure emerging along the reconstruction when you spawn new elements, right? Because the more detailed your XT state gets, the more detailed the distribution of the new spawn location has to be to have the conditional match the marginal.
Mhm.
Does that kind of answer your question?
Yes.
Okay. So so that's kind of like that's the issue that we see with this transdimensional jump diffusion. It works in practice because you can adjust that, but like in our opinion, these jumps into continuous space where you have a jump distribution that's say like a Gaussian conditioned on the x1 value, they require you to ask a lot of your model or you violate your conditional marginal matching. And sometimes that's okay because diffusion models are quite good at fixing issues in the path, but we really wanted to avoid this mismatch where you have to either ask your model to do a lot of work or you have to suffer a mismatch between the marginal and conditional distributions. So the kind of lesson here is if you want to insert an element, you must not condition on x1 when doing so. Right? That's what causes this problem in the first place. Because then when you condition on x1, you get a mixture of all of your data distributions for where that element can jump to. Um, so that was one approach that was handling variable length states, and there's another recent one in the discrete domain called edit flows, which is also a very nice paper. So how edit flows works is you augment your state. So you have an x0 sequence, right, and an x1 sequence, and they don't have to be the same length. And you build an augmented sequence that has null tokens inserted into the x0 and the x1 state so that they become the same length. And then you run a conditional process on the matched elements of this. So your sort of conditional bridge to sample the stated time t is now just working column-wise independent on these sequences that have the null tokens. Right? And this actually, to do this, because you're still trying to learn a model that takes in a sequence without these null tokens and then outputs rates that now uh, behave kind of in the augmented space. You need a theorem that kind of expands flow matching to handle these auxiliary processes. So in this case, you can think of your augmented state evolving under some auxiliary process, and then what you're doing is you're marginalizing over all possible arrangements of your auxiliary process when you're learning your rates in that are operating on your actual sequence without those null tokens inserted. Um, and again, if you take this construction and you think, well, what does this look like for continuous elements? Things get tricky. So the one is there's no obvious single continuous analog of this null token, right? So like if you're building a protein, you could take the global zero or the centroid or something, but that would be quite weird. Um, the other is that just like in the transdimensional jumps, the the sort of spawn value when something emerges, because like if you think about this construction, when you have a mutation from a null token to a real token, that is actually an insertion from, that insertion loads onto the preceding token. And so the element, the model at the sentence position is going to actually be outputting a distribution that must now parameterize the insertion of a new token that will have a whole new state, right? And that's in the continuous context, that's equivalent to placing a point at a new position in your continuous space. So if you just try to adapt this construction straightforwardly continuous to continuous values, you run into the issue where you're placing something via a distribution that's conditioned on x1, and you'll have to model an arbitrarily flexible mixture. It's not a problem in the discrete case because discrete models are great at assigning a logit to each of the possible values in your token space. Um, so this again doesn't naturally adapt to the continuous case. The other issue is that this auxiliary process theorem is that justifies edit flows is only written down for the discrete spaces, basically. So like, where does that leave us, right? So this is kind of where our jumping off point was while we were building this. Like insertions have this problem where you can't place something somewhere useful when you're inserting it, right? So our solution that you'll see how it works is instead of inserting by placing it to a new point, you insert by just duplicating the element at its current value. There's no flexibility about where you're placing it because it's fully deterministic once the event that splits it triggers, right? Then deletions, well, there's a mild problem that there's no reasonable single null element in like the edit flows construction. Transdimensional jumps doesn't have deletions, but if you look at the edit flows construction, um, the solution to this is that, well, you can take elements in your x1 state and duplicate those and tag them so that the conditional process will know that they should become deleted. So that's like a small trick. So if you ask what does the shape of the solution look like, you'll have a model that will learn a per element rate of splitting, a per element rate of deletion, and the base process, which is how the elements change when they're not busy sort of splitting or deleting. So branching flows is one construction that lets you learn these kind of three terms. Um, so I'm gonna switch in. Are there any questions at this point before we dive into the actual branching flows construction? Yeah, go ahead.
Yes. Why do we need a rate of deletion? So now in your construction, or wouldn't it be enough to have a rate of splitting to end
Yeah.
up with variable size objects?
Yeah, so you can do this entirely with splitting. That was the first thing we built was just the splitting only version of this. It's very easy to generalize it to include deletions, and the argument for in favor of them, we haven't done a lot of like empirical comparisons to justify like which one is better. The argument in favor is that if the model overcommits early and inserts an extra state, it can fix that via a deletion later. If the model finds itself with an XT where one extra element is really inconvenient, but it doesn't have the ability to delete, then it's stuck. There's nothing it can do about that. Um,
Mhm.
so it's a little bit similar to the argument about the pure unmasking discrete diffusion. You unmask a token to its final value and you're stuck with it forever now. It works quite well in practice, but there are some situations where giving the model a bit more flexibility to undo early moves can be useful. This is a tunable thing. So in our code, you can just switch this off if you don't want deletions, basically. Yeah.
Yeah, I guess I'm a bit confused how the um s- mm, like you're now in or your forward process now has insertions, right? It's insert things. And then what is
I,
the
I
number
haven't
of element?
I
Hmm.
haven't explained that yet. So I'll explain
Okay,
more
let's
when
just
I
wait.
when I walk through the construction. Yeah. Okay. So basically, what we do is we exploit this latent Z in generative matching a lot. This is in general, we think this is an extremely useful thing that's quite underexploited. Most flow matching setups, the only thing in Z is like one X1 value. If you're doing some optimal transport coupling, you can sample X0 and X1 jointly and put those together in Z and use that to kind of manipulate your sample paths. Um, but here we really go like wild with Z. So the idea is Z must include an X1, but it can include anything else that shapes the conditional path. So you can put things in Z and use them to do whatever you want with your conditional path. And we do quite a lot of that. So this is you're gonna have to bear with me when I walk through the construction because there's a lot of detail, but it all kind of ties together in the end. Right. So this is branching flows and how it works, right? The first thing you have to understand is what goes into Z, and then you have to understand the conditional process, which is what we do with Z. So in Z, uh, you sample X0 and X1, right? That's straightforward. X0 is a sequence from your data distribution as ordinary. X1 is a sequence from your data distribution. X0 is a sample from your base distribution where you can just define a random, per element distribution and then a random number of elements. Like you get to pick that. It can be one element only. It can be some distribution over a number of elements. It doesn't matter, right? Then what you do is you add these to be deleted elements into X1, and that gives you something that I call X1 plus, right? So in this little example, which is everything that goes into Z, your original sequence was this X1, X13, X14, X15. So these are ordered, and we've inserted this X12 star here, which is red because it's a to be deleted element, right? So you get to pick how you do that. You can add none of them, you can add lots of them. It's kind of up to you. The one constraint is that if you sample X0 from some distribution whose size you want to be able to vary, then when you add to be deleted elements, you must add more than there were in X, so that your total length becomes greater than X0. So that's one of the arguments for including deletions is that it lets your X0 distribution sometimes be longer than X1. So you can have X0 distributions that don't just start with a single element and grow. You can start with something that's roughly the right length, but they can either shrink via deletion or they can expand via branching, right? So you sample X1 and X0 and you add these to be deleted elements via whatever scheme you want. You have to say where they go in the sequence and you have to pick what their state is. Their state is from the same space as your elements, and you can just kind of pick random elements and copy them, inserting them in as neighbors, or you can perturb them if you want. If you have the discrete token, you can set it to a mask or dummy value if you like. There's total control over this, right? Yes, go ahead.
Okay, so this means that we cannot like you now sort of sample the position of these to be deleted elements with some scheme that you define.
Yeah.
Okay, this then means that the distribution that you're training on, um, or like how can this distribution of positions be arising in your forward process when you roll it out, or in your generation process?
That's this thing on the right-hand side. So we'll get there.
Oh, sorry.
No, no, that's fine. There are quite this is a more complicated construction than a lot of flow matching setups. So there's a few things that all have to be in place before the big picture kind of makes sense. Um, okay, so now you've got your x1 plus with these to be deleted elements, and you've got your x0, right? And then you sample trees that couple x0 to x1 plus, right? So I've represented those as these little brackets, right? They're trees that have the sort of common ancestry patterns, but you don't have any branch lengths. And if you do phylogenetics, we're a phylogenetics lab originally, so you're used to thinking about trees with branch lengths. At this point, these trees just have topology; they just have structure. There's no lengths in them, right? So well, what are the constraints on the trees, right? They must be planar. So you can't take, say, the third element and the fifth element and make them form an immediate common ancestor, right? That would violate the arrangement here, right? There must be one tree per element of x0, right? So this sounds like it's going to be annoying, but it's actually really easy. The scheme that's the simplest to build is we call it neighbor coalescence. So you start with the elements in your x1 plus state, and you randomly pick adjacent neighbors, and then you coalesce them into a single node, and you repeat that until you wind up with a list that has as many elements as are in x0, and you stop, right? And that gives you a set of trees where there's one tree per x0 and all the trees are planar, right? It's also really easy to impose other structure in these trees. So if your state elements have some natural grouping, like proteins in different chains, you can make the tree coalescence respect the chain structure. So you never sort of merge two elements across different chains, and that links to how the generative process works. You can also, like if you're conditioning on fixed sequences, you can prevent coalescence across the fixed boundary, and it's quite a useful thing with a lot of flexibility to do, right? So now you have x0 elements, x1 plus elements, and you've got trees that kind of couple the x0 to the x1 in this one-to-many form. Um, and then the next thing we have to introduce is this notion of anchors. I did say bear with me, there's a few things here, right? So an anchor is a state that you stick on the internal node of the tree. It's from the same state as your elements live in, right? And so if here's a tree here, this A6 is some anchor that lives on this common ancestor of these two nodes. So the same for this A7, this A8 is some anchor that's the common ancestor for this node and that node, right? So these anchors are going to control the behavior of the state over the internal branches of the tree. So so how do we choose them? It's a little bit like the how do we sample the to be deleted elements. You get to pick any scheme you like, but some schemes will be useful and some schemes will not. So so one kind of generally sensible approach is you set the parent sort of anchor value to be some merge operation of the two children. So for Euclidean states, merge might be a weighted average, right? So if you have two values, the anchor will be at a point in between them, right? For manifold states, it can be a geodesic interpolation. For discrete states, when you merge two elements, you could say set always the merge anchor as a dummy value. And then a general strategy is when you merge two states, you could pick a weighted sample of either child, maybe weighted by the number of descendants they have. You don't have to make the anchor state be some new thing. It can just adopt one of the states from one of the children. Like you get to pick any scheme you like, but good schemes will correlate the anchor state with that of their descendants, right? And that's like the reason that is the case is because what the anchors are doing is they're controlling the process of like they're controlling the generator, they're controlling the flow of the states along the internal branches. So if this x0 is going to transport and eventually become these three x1 states after splitting, what you wanted to do is start off moving towards their average, right? That's going to like it's going to be a nice way of controlling your overall velocity. So if you recursively build this A7 to be the average of these and this A8 to be a weighted average of this and this, then this thing looks like the average of these 3 points. And when your x0 is moving along this internal branch, it's moving towards the average of all of the points it's going to wind up at, right? Um, so how exactly does that work? And the idea is that we just pretend the anchors are like X1 elements. Like when you're defining the flow process, these anchors behave exactly like they would if they were an X1 element, but they only operate upon the internal branches, right? So this is used in the conditional process when you're sampling the next state. I'll walk through exactly how that works, but you're basically using the anchor along these internal branches until you hit a split, and then your elements duplicate and run down the separate branches, pointing towards their new anchors, right? And they're also used to extract the training targets when you're training the model, because what you're doing is you're trying to, if you formulate this as X1 prediction, which we always do, you're predicting the anchor state when you're on an internal branch. So when you're on a terminal branch, your element here, your model is trying to predict where it's going to wind up at the end. But when you're on an internal branch, the model is trying to predict what the anchor state is when t equals one, right? So we kind of build this tree and we decorate that with these anchors. And then we put everything. We put this x1, x0, the to be deleted elements, which are sitting in this x1 plus, the tree itself and the anchors, they all go into Z. So that's all in Z before our conditional process is even started, right? Um, so as I said, it's a much more complicated construction than the sort of standard thing you do here. Right. So now we can talk about what the condition. Yes, go ahead.
So we would sample, or now during training, I sample my x0, I sample my x1, and then I sample this sort of tree. And the tree is defined by sampling some to be deleted elements. The to be deleted elements, they're always close to my end state. So that, like, I sample sort of little atoms, for example, that are then next to another atom in a Gaussian. And then I now have this new set of elements. And then I have some probability distribution over trees to construct. Um, Wait a second. When I sample my x1 and my x0, then how many elements are there in my x0?
Yeah.
How many dimensions?
So you get to pick your x0 size distribution. The constraint on the to be deleted elements is that you must add enough so that your x1 plus is always greater than or equal in length to your x0. So you can, like, the one scheme we use is we say you draw your x1, you draw your x0, and then you take the max of those lengths and you
Hmm.
add, you could get 20% more than that, or you pick some number, so you'll always insert some to be deleted elements, and then you insert those into x1. Kind of what one of the schemes we use is uniformly duplicating elements, in our sequence. Um,
Hmm.
and then that,
And we currently don't know when these will be deleted
yeah,
and like how these will be deleted, so to say. This all comes now in step two on this slide.
yeah,
Okay,
exactly.
and then,
This is all before the conditional process is even started.
yeah.
Yeah,
Then we have our anchors. Our anchors are now always associated with a 3D position as well. So, for example, here A7 would be the mean of the position of x4 and x5.
yeah,
And then AS would be the mean of the position of A7 and x3.
yes,
Yeah. Okay, so now we have this tree, we have all of our additional anchors with additional positions, and we have all of our additional to be deleted stuff.
yeah.
Alrighty.
Okay. So now we have to define a conditional process, right? That will scaffold along this tree and will turn our x zeros into our x ones, not our x1 plus with the to be deleted, but our actual x1 with the to be deleteds eventually removed. Right? So to do that, what we have to do is you can see how this is going to look recursively. We adopt like this conditional independence assumption where the state as it's changing, it only depends on the anchor ahead of it, right? But because the state knows how many descendants are ahead of it, you can use that to parameterize the rate of splitting. So our particular construction is we specify a deletion hazard distribution and a splitting hazard distribution, which control roughly where in time the deletion and splitting events happen, but not how many there are. And the deletion rate is this expression for branches that are tagged as to be deleted and 0 for branches that are not tagged as to be deleted, right? The splitting rate is this h split t, which comes from your hazard distribution, right? Multiplied by the number of remaining splits ahead of you. So when you're here, right? Say you start at time zero, there are three descendants ahead of you, and you're at one state, so you have to split twice. So you have this hazard rate multiplied by the number of descendants ahead of you, so your splitting rate is has some value, and you can use that to sample in closed form from the waiting time until the next splitting event. Right. So it's very efficient to sample down this tree. You start at your x0 state and you say, well, how many descendants are there ahead of me on my tree? I sample a waiting time, and then I update my state in closed form to, the value at the splitting event, conditioned on the that anchor as the thing that's guiding my process, were it to get all the way to time equal to one. Right. So these deletion rates and splitting rates are the thing that actually governs the timing of the events, both the splitting events and the deletion events, which as you run from t equals 0 to t equals 1, pin down where they happen. And they're written in a way that will cause them to always be, 0 if there are no further events, that's by stipulation, and to diverge as you approach time equals 1. So you make sure you'll always consume all of the remaining events ahead of you, as you approach 1. So basically, it guarantees that you'll always have split the right number of times according to the tree and deleted everything that was to be deleted by the time you get to one. So the tree process plus these rates, plus the fact that you're drifting towards your anchors and your anchors on terminal branches are equal to your state values means that you guarantee that your x0 sequence will become your x1 sequence when time equals 1. I don't know if that made enough sense, but yeah. I don't know if you have a clarifying question, Hannes. This has been quite useful so far.
Yeah, so maybe I can just try to spell out. So first of all, let's see what is FH del.
So if FH del is like it's a distribution, right? And what you're doing with this is you're parameterizing a rate.
Okay, so okay, so this the rate must be going to one as we like. I now just want to characterize what this
Yeah.
looks like, right?
The,
The
the
rate
rate
must be going to one as we get closer towards time one.
the rate goes to infinity as you get to time one, but only, until the
Yeah,
event happens, and then when the event happens, the rate goes to zero.
yeah. Okay, so it's like we're making sure that the thing has to have happened.
Yeah, and
And
this particular construction means that the marginal distribution of your events will come from the hazard distribution you wrote down. So it's very easy to use this to say, I want my splitting events to all happen early, or I want them to happen late. Like you get
mhm.
to control that, and it gives you a closed form for the waiting time. So we have the details of all of that in the paper.
Okay, so but FH del is now a distribution, or it's a function that maps from the interval 0, 1 to the positive real numbers, and it integrates to 1, to
Uh,
the non-negative real numbers, and it integrates to 1. So it's a PDF
no, I think it's a
or
cumulative.
define. Are we someone else jumping in here? Okay, so
Small f
the
is
small
a
f is
PDF
a
and big
PDF.
F is a CDF. So
Yeah.
yes,
Yeah,
Hannes, that's correct.
Yes.
okay. And then now if you want to design this stuff, it's very nice because I can now just define my PDF here where I say, aha, I want all my events to happen, like all my splitting and all my deletion to happen either or like, and these can be separately controlled. I want these to happen between 0.25 and 0.75. And for example, a uniform distribution over that interval. And okay, then I think, yeah, this is all set. Also, talking about the tree now again a little bit. So about what's stored in your Z, the association for what x0 belongs to which x1s, like it will always belong to at least one, but potentially multiple x1s, right? Uh, how is this determined? Is it like completely random in your tree sampling distribution?
So this is one of those things you get to choose. In the sort of simple version, we do this by this neighbor coalescence. So you just pick adjacent elements and coalesce them, and then that like how you wind up with your final list that maps onto where your X zeros are becomes random based on that sampling scheme. But that that they tend to correlate with the order in the sequence. So an early X1 will map to a few early an early X zero will map to like the earlier X1 sequences. Like it induces a coupling between them.
Yeah, but I mean, how is the X0? Like, is it just in 3D space, this neighbor coalescence,
This,
or
this is
like,
in the sequence space. So these are ordered sequences when you
ah,
when you use
okay,
this construction.
okay, all right. Then maybe back to, so we now understand these deletion and split rates, I
Yeah.
think.
So that they tell you like when these events will happen and they guarantee that you'll wind up at the end, right? And yeah, as I was saying, the hazard distributions allow for this easy control of like you can think of them as schedules of when these events will happen. And you get closed forms for the waiting time until the next event, which is really convenient for sampling this efficiently. It's also convenient for because you have to have the model sort of predict these splitting and deletion rates, and this construction also lets you have the model predict like do an X1 prediction over these. So for the splitting, the model is actually predicting the number of splits ahead of it by time equals one. Right, so it's like an X1 prediction over a split rate, which gets transformed back into the rate via that hazard. And then for the deletions, the model's predicting a probability of deleted or not. And that gets transformed back into the rate via the hazard. And this lets you do, like in our experience, these X1 predicting models, they always behave like they train faster and they're more stable than trying to predict an outgoing rate. Um, and it also gives you really nice losses. You get a Poisson-like Bregman over the expected number of splits ahead of you and just a cross entropy on the deleted or not probability. And Lucas has a really nice sort of little bag of tricks for how to more conveniently set up these kind of things via X1 prediction. So a small plug for his sort of theory manuscript over there. Okay.
What is a Poisson like Bregman?
I don't know if I have the expression in here somewhere, but it's kind of like exactly what you would expect. No, I did not include it. It's in the paper. It's a very simple loss that is guaranteed to learn the expectation of your rate. But in this case, we're learning the expectation of a count at the end and transforming that back into a rate.
Okay.
Yeah. So now, if you want to sample XT, right, the kind of algorithm for that is you start at the roots of your trees and independently you recurse down by sampling the waiting time and then sampling the new state at that event, right? Which is like normally when you're setting up flow matching training, you have your X0 state and your X1 state, and you have a closed form sample for what XT looks like. Here you have your X0 state and you have the anchor, which you're pretending is an X1 value, and you're drawing an internal state over here, which means that sometimes your starting state is not at zero, it's at some time that's positive, and you're drawing a conditional bridge kind of ahead of you. So you do need to have a slightly more flexible endpoint condition sampler for the process you're working with. Um, but the algorithm is you sample your waiting time and then you update your state. And then if the event was a split event, you duplicate your state and you attach each copy of the state to a different branch and you recurse down there. So it's like this recursive sampling scheme it's still linear in the number of elements at the end. It's very efficient to sample from. Um, and what you do is you collect any surviving elements at the time that was requested. So if you're sampling XT, you recurse down, and then if the next event was kind of ahead of this T, you only sample the next state up until that T. And if a state gets deleted, it gets removed from the list. And you also collect for every element what the anchor was ahead of it. So for this element, the anchor would be the actual X1 element ahead. But for this element XT3, the anchor is this A7, which is going to be something like the average of these two. And those anchors that you collect one for every element in your XT state become the training targets in your losses. So when you're learning the sort of base process and how the state must be changing, you're training against the anchors for internal branches, right? Um, so that kind of tells you what the loss is going to look like, which is the next step because you have to train a model that will output split rates, output deletion rates, and output the kind of generator of the base process. And so the loss you get is this Poisson-like Bregman for the splits, this cross entropy for the deletions, and then your base loss is whatever process you're using, but using the element matching anchor that that was if you were on an internal branch as the target that that's governing your generator for that particular element in the state. And the overall loss you get decomposes very nicely into the sum of these losses. So yeah, there's I've mentioned this base process a few times, and it's really like you can pick your favorite flow matching process. You can put it on, Euclidean states, discrete states, manifolds, multimodal combinations. It doesn't really matter. The only thing you need that's a little bit extra to the standard flow matching setup is you must be able to efficiently sample an xt given an xs and an x1 where s can be some number slightly greater, that can be greater than zero. So you need to basically update your step along internal branches as well, instead of just sampling where your endpoints are at 0 and 1 only. So the processes we use are for our discrete elements, we use like this discrete flow matching, like there's this equation 10 in the DFM paper, which is like typically you start X0 with a mask and you unmask your data distribution, what's your X1 element, but you also allow changes to noise. So it's a little bit noise tolerant. Um, we have for our Euclidean states, we have this Unstein-Uhlenbeck-like process that has a mean reversion term that pulls towards the X1. This is just quite a convenient thing to parameterize. And then for manifolds, so any manifold we work on is this rotations manifold for our protein models. It's also an OU process, but the mean reversion is pulling along the geodesic to X1. So those are all individually like uh, quite ordinary things. But you can now package them in this branching flows and say, well, we'll have this tree and the splits and deletions, and our base process will handle the states, and it's all composable. So there's a little complication, right? That I didn't mention because like practically you can ignore it. But if you're given only a tree in your Z and your current state xt, the process actually doesn't know which element is on which branch, right? Say you have this tree here and there are three elements, right? You could have one that's sitting along this branch and then one here and one, sorry, one here, one here, one here, or you could have one here, one here, one here, because in Z, the timing of the events hasn't been pinned down, right? So there's actually an ambiguity when you have an xt for which element lives on which branch, right? So what we do is, like in the paper, we spend a bit of time on this. We introduce this discrete latent variable that tracks the branch index of each element. But now your process is not Markov in the state alone, it's Markov in the state and this discrete latent variable. And we have a little extension of the edit flows like theorem, which handles marginalizing over these auxiliary variables. But this is an extension because edit flows was only for the discrete x discrete latent case, whereas ours is for the arbitrary x discrete latent case. And that lets you marginalize over this branch tracking variable. And in practice, it means you can just ignore it because in your code, you would be tracking which element went down which branch in the conditional construction. And all you do is you just don't pass it to the model and you wind up marginalizing over what that branch tracking was. So it's kind of practically this is a non-issue, but to understand why it works theoretically, you have to introduce this. Is it close enough to making sense? The other kind of little twist is that in a lot of flow matching constructions, the conditional paths are all independent of each other. But the thing that's different here is that when you split an element, the states that you get at a split event will be really closely related. So if you think about your paths overall, they're now the tree has induced a dependence, right? And so like in the theory, we use a conditional independence assumption where the current state is evolving independently of everything else given the anchor, and that allows us to use the more like familiar element-wise loss. So we don't use the same kind of factorization arguments that they set up in GM. We have like a slightly less restrictive thing that still gives us a nice loss that we can handle element-wise. Um, So okay, so that's the construction. Like before I go into a couple of toy examples, are there any questions about how this works? We've got this, we sample the trees that link the states, and then we build our conditional bridge over the trees, and we learn the split rates while the model's learning to predict the expected number of splits ahead of it and whether the state is deleted, and then it's learning the base generator pulling towards the anchor on the branch ahead of it. And that's kind of that's the whole trick. Um,
Yeah. So the thing with these branches are now you're essentially training the model to learn all possible branches, right? To learn all possible branchings, meaning that this is a very large combinatorial space where, like, the model now, um,
all the model
yeah,
has
no, 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 it's not so large because you do this weird branching or this um,
planar.
coalescent branching where then the model learns that things that are close by. Yeah, the model will just learn this distribution of trees that you define or that you sample from. And this distribution is pretty narrow in the space of all possible trees. So yeah, this is not something that gives us any training inefficiency.
Yeah,
Um,
and like from the model's perspective, it's looking at the current sequence and it's going, oh, I need to add something in at this point, so I'll split this element, right? And it's, or this, I have too many things here, I can delete this one. It's not, it's uh the even if that space is big, it's learning the average, so that it's not necessarily a problem if the space itself is, is too large.
yeah.
Um,
Okay. And now the outputs of the numbers that you're outputting with your neural network for each element. Is it actually a rate or a probability for the deletions and the
Yeah.
splitting?
So the splitting is outputting. You can kind of parameterize it in the log domain if you want. Like that's all numerics tricks. The according to the theory and what goes into the loss, the model is outputting a like an expected count. So it's it's some if it thinks that it's going to split twice in the future, it'll output two, right?
Yeah.
Um, for the deletions, it's we parameterize that with a probability, but with a logit, and it's a logit cross entropy. So
Yeah.
yeah, so it's a very like these are
Okay.
all very like nicely behaved quantities to learn. Um, right? So
Yep.
I'll go through some examples. They might like this is what we were playing with originally. It's S bench. It's like the simplest non-trivial sort of sequence learning thing that involves multiple different states. So you have this underlying sinusoid function and you have a sequence of elements whose positions are evenly spaced in the x dimension and but then the number of them in the start and end points is kind of randomly sampled and their token alternates across the sequence. So a model that learns this has to learn the dependence between the position and the discrete state, and it's like a little toy benchmark. But the reason it's nice is because it lets you see if you use a continuous process that has a little bit of noise, you can actually see the trees that are not the conditional trees, but the marginal trees that are implicitly produced. In the marginal process, the model is not tracking a tree. It's just taking the current state and splitting and deleting elements, but that kind of implies a tree over the course of its construction. So this is a case where like your starting element was here, and as it evolved, with this small Brownian motion noise towards initially it looks like it was heading in this direction and it split and split, and you can see the deletions where the this sort of states run out. And this is just drawing the model trajectory. These are not actually connected paths, they're just little dots for every xt in the sampling sequence. Um, but like you can see from different samples that like the decisions that are made, like if it's going to wind up, your X1 lengths are all different. So you get this kind of decision that emerges. If you have a few early splits, the model thinks, oh, I'm in a state that must have had a large number of elements, and then it it has like a cumulative effect, and the split rates are all kind of higher later on. So you get all of what you'd expect if you think through how this is going to behave. And you can also like look at the flexibility. Like you can introduce longer X0 sequences. So these examples were both starting from one, but if you train a model that starts from some number of them, then some of them don't undergo any splitting at all, but some of them do. You can train a model that's like deletion only, so you have no, in your conditional bridge, you have no branching. And you can mess with the base process. So these were all low noise Brownian motion. Yeah, sorry, go ahead.
So deletion only, didn't we say that x0 must be less than or equal to, like the number of dimensions in x0 must be less than or equal to what we have in x1?
Yeah, so for deletion only to make sense, you basically your X0 distribution must be very large, and then you add a lot of to be deleted states, and like
So the
you
statement that we had before just doesn't apply here for this example.
yeah, it's
Okay.
we don't think that we don't like this particular case, but it is within the space of things you can do, basically. Um, you can mess with your base process. So this is like low noise Brownian motion. This is the OU process we use. That we picked this process because like when we played around with this, if you have like paths with zero noise, that turns out the model doesn't like learning that. It's like not like ordinary flow matching, and I think it's something to do with split events inducing like a tie breaking problem or something. Um, but basically, processes that have more noise tend to behave nicely, and I think it's because if you have a late split, the model needs to induce a fairly like large velocity to get it to the targets. Just because if you have two elements that are apart and you split late, then you have to have a decent move. So processes that have a relatively high amount of like intrinsic noise, it seems to like those more. That's all quite exploratory. We're running on to like an hour, so I don't know, like, does this end or is this one of those things that just keeps going?
Um, I would prefer if it just keeps going.
Yeah, we can do that. So that's like the toy example, right? The th we worked with three real examples. QM9 still a little bit of a toy example, right? They're small molecules. They're not intrinsically ordered, but we impose an order on the atoms using the SMILE string, and we kind of insert the hydrogens within the sequence so that the training target order kind of makes sense to merge. Um, and the state is an atom coordinate and the type label. And so we have our OU continuous process and our discrete flow matching for atom labels, and we train a little transformer. And so now it's the heads on this transformer. It's outputting the coordinates for the atom positions. It's outputting the logits for the atom labels. It's outputting the expected splits ahead, and it's outputting the probability of deletions, right? And we compare like we're interested in how well does this learn distributions. So what we do is we take the data and we look at one-dimensional statistics of the data distribution. We compare our samples to that, and we compared this to we just reran their model for trans-dimensional jumps. We didn't retrain it or anything, just using their pre-trained model because it was on the same problem. And so the other nice thing about these is if you kind of space out the samples, you can also see the tree-like structure in the generative process. So here you can see these atoms splitting, and then the colors change when the states change. And our state changes has this noise, so you can change to one state and then it can change again to something else. Um, uh, and you can see like here is a deletion happening along here. This was trained with quite a low to be deleted rate. And if you look at the trajectories, here this is looking at xt on the left. So that's the current noisy state. And then the x1 hat is the predicted end state as it evolves. So that tends to be much more stable. You can kind of see like the dynamics of the process. And if you stare at these a lot, you can learn quite a bit. Um, in terms of how well it does, uh, like these plots are like this. We take each molecule and we convert it into a fingerprint with RDKit, and then we embed that in 2 dimensions with UMAP, and then you can kind of look at the distribution of your molecules and see how well does the generated samples match the real ones under this kind of arbitrary projection into 2 dimensions. Um, and the QM9 samples and the generated samples, they overlap a lot. It's not perfect. Like there's a little shift in molecular weights here. Um, but if you look at trans-dimensional jumps, uh, if you actually quantify the distribution matching, we do a fair bit better on most of these. I think I have a table here. So there's some that are similar, and there's some where we're doing substantially better than trans-dimensional jumps. We suspect it's due to some of the issues we discussed earlier. if you stare at the UMaps, you can see where the density is missing. So here, this is the UMap of the QM9 samples themselves. Here is branching flow. So like if you look at this region, there's a little cluster with a high number of carbons, and that's matched quite well. But transdimensional jumps, the density is kind of just missing, and that shows up in the statistics for these things as well when you look at the one-dimensional projections. So we think we've got a quite a good distribution learner, at least on this example. So the next thing is discrete only antibody sequence generation. This is a nice toy discrete problem because things train fairly fast. And it also lets us compare to discrete only models. So this is also trained with a straightforward transformer with rope for the index, and you're outputting your amino acid logits. This is only discrete, so they're just logits, then the expected splits and the probability of deletion, right? And our metrics here, we compare the distribution matching on various one-dimensional statistics, so the same as QM9. But then we can also, we train a large autoregressive model and we can look at the perplexities of the different sort of diffusion or flow samplers evaluated under that model to see how nicely things train. And we compare to an oracle length model, which is like if the model always knows what the correct length is at training time or sampling time, so it's like it's got this unfair advantage. And then we compare to edit flows with a caveat. This is our own edit flows implementation, so there could be any number of things wrong with it, causing some performance differences. Um, so in terms of the oracle length comparison, our training is a little slightly slower in the beginning, but we quite quickly get into the same perplexity range. So this is like as sampling's going, the generations we get, start looking quite similar to an oracle length like vanilla discrete flow matching model. The embeddings look very comparable. The statistics on all the sort of one-dimensional quantities look very comparable. Basically, we learn the same thing as an oracle length model without having to tell the model what the length is, right? Comparing to edit flows, our perplexities kind of hover a little bit lower than the edit flows perplexities. And this is interesting to us, like the edit flow seems like it does just as good a job at learning the length. So the total sequence length matches very well for edit flows and branching flows to the true data. And the CDR3 length, which is a sort of subunit of this that you can identifiably pull out, also matches very well between them. But the metrics that are based on the sequence content, edit flow seems to do worse, right? And if you tabulate this, like the length matching, edit flows, branching flows, and oracle length are all very similar on the length metrics, but ones that include the sequence content, branching flows and oracle length are similar, but edit flows is substantially worse. Again, that caveat, this is our own implementation. Who knows? Who knows what could be going on there? We have some hunches about what's going on with edit flows, but maybe a little too early to talk about them, right? So then the kind of domain that we're interested in is protein structure and sequence generation. And the model includes sequence, but we don't really like this is not kind of a we're not convinced this is necessarily the right way of generating sequence, but we just parameterize it like this because we think it might help the generative process for the coordinate sampling to see sequence while it's getting generated. And then when you condition on other structures, they have sequence and everything's consistent. Um, our data is the PDB. Our state is we use an AlphaFold 2-like representation where you have a Euclidean position for an amino acid backbone frame, and then you have a SO3 rotation for the amino acid backbone frame, and you have a discrete amino acid label, right? And so we have Unstein-Uhlenbeck on the centroid, we have this manifold Unstein-Uhlenbeck on the orientation, and we have discrete flow matching again with a noisy process on the amino acid label. And we took a model that was from a previous paper of ours, and we fine-tuned these heads in. So we didn't train from scratch. We took a pre-trained model and we just fine-tuned in split and deletion heads. Um, and we don't really like the protein metrics. We don't believe in the refolding very much. So the only thing we care about is does our model with splits and deletions exhibit like correct looking geometry? Um, oh, there are questions popping up in the chat. I don't know if I should be answering those as we go. Uh,
Yeah, so there are some have been answered by your colleague, I guess. And um, I would maybe finish now
I
until
can do that.
we, yeah,
So what we do to Let me show you some examples first, and then I'll talk about it. So this is a model, like we've trained a few different versions of this. This model starts off with Poisson 20 X0 states and then generates, however many at once. It can wind up less, it can wind up larger. And again, this is the XT state on the left and the X1 hat on the right. And if you look at these, like you can see where it's inserting the length is sometimes quite interesting. So in this case, it makes these nice three domains, and you can see it like distribute residues along the linkers between them and change their size and everything like over the course of generation, which is part of the point of all of this. The model also does some things where this is something it inherits from the previous model. If you ask it to generate two chains, it very frequently assumes they'll wind up being dimers, and it spontaneously generates these things that look like symmetric dimer copies of one another. And then it's like the process has learned that the lengths must wind up matching at the end. Um, this is an example where, we're conditioning on these two chains and generating two other chains. And I'm actually just going to pause this because you can see there's a domain here in blue and a domain here in blue that are part of the same chain, but there's no linker between them, right?
Hmm.
And if you watch as this process goes, it like winds up building the linker and adding elements and controlling that overall linker length until all the geometry lines up. So so this is like a nice motivating example because if you think about what like an ordinary flow matching model would have to do is it would have to commit exactly which of the residues from the X0 state are going to wind up in the domains and which are going to wind up in the linker before it has a very good understanding of what that final, endpoint is going to look like. So this almost like we think this makes the learning task easier because it doesn't have to like know very early in the flow matching exactly how things are going to be distributed for these things that have, you know, are separated domains or have that kind of structure. Um, this is another example where we condition on parts of a chain. We ask it to fill in the thing. So it's just an easy case to see it building up things that span and decide how many elements go in between. Um, and again, this is the template that we were conditioning on was a dimer, so it builds the thing as though it's a dimer as well. This is like if you condition on everything else and ask it to build the CDR3, you can see it like dynamically grows the size of the CDR3. Um, so like one of the questions is like with all the splitting and deletion, are we still like having things that are sensibly protein-like? Um, and our model, like our base model, has the same thing. It doesn't generate things that are easy to refold, right? But so the metric we use to ask, does this have geometry that's consistent with the folding model, is we call this multiple sequence alignment SCTM, where we generate a large, we'll say 100 sequences via MPNN from every chain, and then we pass those into bolts or bolts two or something, and we ask it to refold, and then it's basically getting a pseudo multiple sequence alignment, which encapsulates some of the sort of a amino acid like pseudo coevolution properties, and then can refold the structure. So it's a softer test than asking it to refold with a single sequence, but I think refolding with a single sequence is asking like you're asking to solve a complicated folding problem uh, for these things that don't match to anything in the sequence databases. So our things, at least when you give it hints in the sequence alignment, bolts will refold them to something that has basically the same geometry. The only cases where you depart, like you can see most of these SETMs are high. The cases where we depart are when our thing has a flexible linker and the individual domains are folded correctly, but we have a mismatch in the things. And then occasionally our model puts two chains that are separated apart, and then the refolding can't get that right. So at least with the splits and deletions, it's generating consistent geometry, and these stats look real similar to what the base model without the splits and deletions does. So we think that they're at least like they're not hurting. It's using them appropriately. Um, this is if you ask it to generate a CDR3 conditioned on RBD receptor binding domain from SARS-CoV-2. So you condition on the blue part of this nanobody and you say generate, like you delete the green bit, you add a single state and you say sample that. The top CDR3s are sampled with the RBD present and the bottom ones are sampled without. And it's pretty good at like it avoids clashes of the atoms, even though it's only seeing the backbones. Like it's doing kind of sensible things. There are no great metrics for these as far as we're aware, but it's at least producing plausible geometry. Um, Okay, so to wrap up, like we've got this is all implemented in Julia. We're weird like that. We have everything kind of interoperable layers you can pick and choose and reuse. We have a package that handles like the base processes. So we were building that before we did this. Like you can say my state is discrete and manifold and Euclidean, and just compose your base processes, and you'll get a flow over that compound state. And then branching flows, the package itself wraps that and imposes this tree structure and does all the sampling and training. And we have a repo for the protein models that should be up and working now. You can just go there, pull the models, and it'll pull them from Hugging Face, and you can sample from them. So that's all up and working. And this is our ecosystem. We kind of want to convince everyone to start doing this stuff in Julia, which is a bit of a long sell, but yeah, it has its advantages, especially when your bridge constructions get more intricate. Writing those loops and recursions in Python can get a little slow, but in Julia, it's all very efficient. So you never have to worry about adding extra complexity to the conditional process, basically. Um, yeah, so that's basically it. Branching flows is a capable distribution learner over variable length sequences. It scales nicely to beyond toy problems to things like proteins. The conditional construction allows many new tricks without needing to develop. You don't need to do any new maths to do something new. So you can change the way you sample trees and bake something into the conditional path just by sampling the trees differently. The same goes for the anchors. We have a little set of tricks we're kind of exploring there. Um, and the next steps, we want to try and scale the current protein models. We've already got them. We've got versions that are available now that you can condition on things. So you can say make something that has the same like rough size and secondary structure composition as a nanobody, and it'll design things that are nanobody-like. So that all is working at least initially quite well. Um, and then we're quite interested in expanding to new models. We think it's promising that you can fine-tune these split and deletion heads in, because it means we can adapt existing models. There's some challenges, like BoltzGen has a trunk that takes in we think, like we takes in the designable uh, parts of the sequence that you would normally know. You have to specify how long they are. And so if we were using BoltzGen for this, we'd have to run it through the trunk every single step of the sampling. So there's some architecture choices that turn out to be a bit limiting, um, if we've understood BoltzGen correctly there.
Yeah.
Yeah, and we're
So I
also
think
sorry, go ahead.
if you're done, then I would go ahead.
Okay. No, well, yeah, that's basically this is wrapping up. We're playing with some all atom models, and we want to try and do some interesting things with these. Acknowledgements to the lab, especially Hedwig and Lucas, and then yeah, the Theodore ported edit flows. Jack did a lot of the empirical work. Aaron worked with the protein models, and Anton does a lot of the like ecosystem and building and layer development and architecture stuff. Um, yeah, so that's basically it. Slightly over time.
Amazing. Okay, many questions. But before questions, let me say I think this is very lovely, and I love just the the construction, the clean. Okay, I mean cleanness. There's definitely things where one can be sad about us having these additional distributions from which we need to sample our positions for the to be deleted elements or stuff like that. But it's just lovely to see a step towards or such a nice big step toward yeah, just size independent, and as you write it, true all atom generation, right? And
Yeah.
it's pretty obvious how this could now happen. And now for the true all atom generation, we also do not actually need the to be deleted tokens. And unless we want to still keep the So I guess the true all atomness is independent of the um, let's say variable number of residues aspect. And yeah, the you asked, for example, about Boltzmann. We have the trunk in there, and the trunk includes the generated part, right? I don't think this is an issue. It can just be your X0 distribution, many tokens. So the generated part can just be as many tokens as in the X0 distribution for the generated part. And then you process that and you just broadcast that conditioning that is in the X0 many designable tokens or so to the other tokens that are
Yeah.
going to be designed. Yeah,
So
I
then
think,
it depends on exactly what that trunk winds up learning, because if it learns something like pairwise, expected pairwise distribution distances,
yeah,
something like that, then when you take one element and you broadcast that to the whole designable range, that could you make the diffusion module work a whole lot harder than it's currently doing. So I worry about, like, sure, if you train from scratch, anything will work, but if you try and fine tune it in and make the trunk behave very differently, and make the diffusion model work much harder than it currently does, I think there's an issue there. Like, I think there'll be clever tricks, but how hard you have to work to fine tune it in will, yeah, depend on those sorts of
yeah.
things.
Okay, but let's get back to your paper. Instead, so I am saying and still saying this is absolutely amazing, and I just love seeing these animations. And I would advocate for you putting one of your generation animations where you're making your protein or so, and it's infilling the chain or something like that at the beginning of your slides already. I think that would catch a lot of attention and. Yeah, but questions. So let's consider the scenario of generating small molecules, for example, right? If I now, like the model now decides to generate a big small molecule instead of generating a small molecule. If it generates a big small molecule, then the X1 prediction will always suffer more from being from having the structure being incorrect than if you generate a small molecule, right?
I'm not
Because you're
I'm not sure. You mean
like
in having the so you're talking about generating a small molecule conditioned on a protein structure or
no,
something.
no, no. We're just doing QM9, for example, now, right? And then isn't it the case that generating like your MSE loss or your structure loss, it will be higher if you generate big small molecules compared to when you generate small molecules.
We average per element.
No, 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 that's not what I mean. It will be higher because the structure is inherently harder to predict for a larger small molecule than for a small molecule. For your water, you will always get the geometry right. It's trivial to get the geometry right. But if you now have your complicated, um, I don't know, cocaine small molecule, then it is hard to get the structure right. And then it'll be easier for the model or like the to minimize the expected loss, you would rather um, tend toward generating small molecules. Is
No,
that not happening?
it doesn't do that, because what it's doing is it's learning with the conditional paths. So during training, it's got the current XT in the conditional path that you've sampled, and you're predicting the actual X1 that was paired with that, the number of splits ahead, and the position of the anchors or the final elements. So it can't cheat during training and decide to sample smaller things, right? Because the loss is always taken in the context of what the length of that current X1 was.
I see, right, because it's not the geometry that's uniquely determining. Yes, it is instead the yeah, because these are yeah, it's in a different, it's in the latent, it's in the sets, the information of how many things there will be in the X1. And okay, okay. Yeah, that's nice. Um, then let's maybe get to some questions that we find in the chat.
Yeah,
What is the
I'm gonna
mhm.
stop sharing because I can't actually see. Okay, now I can see the chat.
What is the disadvantage to separate the distribution on the length of the sequence and the generation of the structure? So, um, yeah, maybe you
Uh,
go ahead with that first.
so this is like you're saying, why don't you just sample length from a length distribution and then sample the structure conditioned on that length? I think if I'm understanding the question correctly. The answer,
Um, I think that is kind of clear, but maybe the interesting piece I would say is, do you now not lose some sort of controllability over the length that you want to generate? What if I want to specify that I want a certain length?
yeah. So this is I consider those two different questions. Uh, the disadvantage of sampling length and then sampling the structure is that it's very hard to come up with a model of the conditional length of something, right? If you want to solve some design task, then if you're not building the length during generation, then you have to say, well, I want to make something that binds here. I have to build a whole model of how the length will depend on that. If you want to scaffold an epitope that requires filling in six different things, you have to build a model that must predict just what those length distributions are and sample them in a way that captures all of their mutual dependence before you can generate the sequence. So if you're doing just pure unconditional generation, then yeah, you can train a length model because it's just learning a one-dimensional distribution. But as soon as it gets more complicated, then I think it's a proper disadvantage. Um, I hope that answered the question. Then for your version of the question, Hannes, which is you lose controllability of the length. That you fix by conditioning. So if you can add a conditioner and say I want things that are smallish or biggish or largish, and you can put as much control over that as you want, just like you can condition with everything else. So one of the models that we have up now has that. And you can pull it in and you can basically say, I want to inherit the features, which are quite coarse, from this domain, from this PDB, and I want to design that as a binder to this, and it'll basically take those and generate something with similar stats. So similar contact order, similar secondary structure. Not, it won't look like the same structure at all, but it's a nice way of conditioning on those sorts of things. So it's you solve the length controllability problem that way, but without
Yeah.
having to tell the model you must be exactly 96 amino acids long, which I think is where the problem comes in.
Hmm. Nice. Okay.
So then
Then,
were the antibody models trained from scratch? So this we had this previous paper where we have this, it's like the simplest possible flow matching model you can write down. It's just an IPA stack um, with some cross IPA and self-conditioning that really seems to help. And so that was trained first. That was without any splitting or deleting, and we fine-tuned the branching flows, splitting and deleting heads into that architecture, and that still worked fine. So the model's already representing enough to know when it needs more elements and when some must be deleted, because that fine-tunes in like 2 days. Like you get good branching flows, sampling behavior with a very quick fine-tune on top of an existing model.
so the last question that we have in the chat, I think, is about how much, like, do you now sample a different tree at every training step for your X0 and X1?
Yeah. So what you do is your training step, you work in batches. So you draw a batch of X1s, right? And for each X1 you sample an X0 and you add in your to be deleted yeah. And then you add in your to be deleted elements to your X1, and then each one gets a separate tree. So one tree gets used for a single time slice. You don't use the same tree over and over again, basically. So you try and maximize the stochasticity of the trees. Otherwise, you'll probably get some weird training dynamics, and you might overfit to particular paths for some kind of proteins or something like that if you reuse the trees.
Mhm. Okay,
There's
very
a
nice.
question about neighbor coalescing. Maybe I missed.
That was the one about the like there was do you do the neighbor coalescing for every training step anew or do you like reuse it?
Okay. So, okay. Thank you. Yes.
Yeah, maybe why okay, so I see that Julia maybe has some technical advantages and niceties, but it definitely um like I would bet a lot of money on you not being able to shift the community toward using Julia. So why do
Yeah,
you keep insisting on it?
I wouldn't take that bet. I would lose it. Um, so it's partly it's what we work with. Uh, it's also there's we gain some benefit from being forced to kind of do everything from scratch, and doing everything from scratch in Julia is a little bit less painful than doing everything from scratch in something like Python. And partly this is a bit of a crowded space. So anything where you are working in a framework where things behave differently, it lets you do some new things. So like I don't know that we would have tried something where the conditional bridge involves like recursing down a tree that can have hundreds of branches
Mhm.
on it in Python because you'd wind up lagging the GPU and you'd have to spend a lot of effort, making that fast. Other instances like our I don't know if the original I'm trying to remember which one. One of Alex Tong's uh, uh, protein papers that has an SO3 diffusion, where they spend quite a lot of effort deriving this isotropic Gaussian SO3 distribution for their conditional bridge approximation, because you need that to get it to do sampling. In Julia, you can actually just step through multiple steps of a diffusion on SO3, and it's so fast that you don't lag the GPU. So there's all these things that you get nicer behavior because you can just loop through stuff much faster, and you're not kind of constrained to a set of things. So um yeah, it's a little family of things, but from our perspective, like I think if you make a tool that works by itself and it can do something new, which we haven't done yet. Like I don't think that everyone should go and start using these for design competitions
Yeah.
or for, in the wet lab, but we might get there. Then I think people will use it because it's not that hard to
And
use, and the packaging system is
yeah,
really nice. Like it's you don't have to fight weird dependencies going missing. Like everything's pinned down, so you should just be able to package.add and run, and it works. So in that sense, I think if we get something good, then we'll get people using it like in practice. But yeah, we're not going to convince the computational people to all start developing in this. I agree with you there.
yeah. Okay. No, this is very nice. I love it. And yeah, do you want to say any last things before we call it a day?
No, I'm happy, and I don't know if any of my team want to unmask themselves and say hi or something like that. I know some of them.
All undergrad students, is that right?
There's one master student, but the main people here are basically like Hedwig was in high school last year, Lucas was in high school the year before. They both have grad program applications out, so if any of those come across a
Okay.
desk or something, you should pay attention to them.
Including at MIT?
One of them might. I don't know what I should disclose
Okay.
and what I shouldn't. Yeah,
Then these people shall feel free to reach out to me and let me know if some of them are also at MIT.
thank you. I think they're listening now, so they know that already now.
Good.
And thank you very much for the invitation. We don't go like we'll probably start now, but we're not really on the conference scene or anything, so it's good to be able to chat to people in the community.
Amazing. Good. Then, thanks so much for joining. I hope we stay in touch. I'm sure that like we're definitely interested in messing around with some of these things in the Bolzgen area as well. And then it would just be very natural to collaborate on that.
We would love that. We've started actually porting Boltzstone to Julia, because partly because we don't understand something until we've ported it.
Okay,
But I'm sure we'll bump into some stuff where we'll probably quite soon where we reach out
great.
and ask for a conversation about that.
Then I will reach out separately and so we can maybe see how to chat best if we use Slack or something like that. And yeah, then thank you all for joining. And thanks, Friend of the Sun, for joining as audience in the reading group. And see you all, yeah, I don't know, maybe next Monday.
Thank you very much.
Bye.